Everyone. So it's our, I don't remember, maybe 15th or maybe 12th of the NLP interest group meeting. And this time we have our Robert Tang from our computer science department to join and give us a presentation about large language model and agents. Yeah, so maybe you can give your self-introduction, then we can start.
Yeah. Hi, afternoon, everyone. So it is a great honor to be here and share my work. So I'm a Ph.D. student. I'm about to enter my third year. My advisor is Mark Gerstein, and it's a great honor to have the opportunity to share my work with you. I would like to extend my huge thanks to Dr. Xie for inviting me, and also as well as to Dr. Xu and Josh for their support. So today my topic of my presentation is AI scientists, empowering biomedical research with large language models and AI agents. So really today's outline, I would first share some background by starting with some personal stories. And then in the main part, I will share some papers, some of my recent work. The first contribution is called MediAgent. So it is it demonstrates how LLM can participate in complex reasoning. And in part two, one burning question is can LLM do codings like us? So Biocoder and ML Bench, their two work highlight how LLMs and AI agents are being utilized to do biomedical data science and code generation. So in the last part, however, there's need to address the risk associated with deploying AI agent in scientific domains. So first, I would like to share a personal story with you. So Bonnie is my dad's Sharpie dog. So Bonnie was born with entropion S. It is a genetic condition in which the eyelid turns inward. So this condition also causes the eyelashes and skin to rub against the eye surface. So my dad and mom, they initially took her to a local clinic, but this local clinic can only handle some simple surgeries. So due to her condition, Bonnie was referred to a specialized ophthalmologic hospital. So at the eye specialist hospital, those doctors conduct different examinations and provide different recommendations. So actually, some doctors think we need to do the immediate surgery to her because necessary to prevent further eye damage. And some doctors suggested waiting until Bonnie was a bit older because they think it might have some risk. After she grew up, the risk might be lower. So to make the best possible decision, Bonnie and several doctors had a discussion. And after the discussion, they think we need to wait a few more. So after around 6 months, we done the surgery for Bonnie, and it was successful. And Bonnie's eye problem never come back. So this experience highlights the importance of discussion in medical decisions, especially in complex medical decisions. By multiple decisions, Bonnie received the most bad. So actually, different doctors may have different perspectives. So I'm not a medical student, but according to an article in Nature Medicine, Nature Reviews, they call it MDT, multidisciplinary meetings have formed to be an essential component in the management and healthcare, the state of care of patient. So actually, MDT meetings bring together specialists from various fields to discuss complex cases and make the treatment. Okay. And there's an example, how different people make decisions together is an interesting problem. Let me share this example. The definition might be familiar to many of you here, the Ph.D. defense. I assume the majority of you have successfully gone this process, but I did not. So here we need to identify two main issues here. So the first challenge is there are two issues. The first challenge is how to select those members, the community members. The background of your community members are important as they will question you from different perspectives. Here, and the second question is how the committee members discuss, the committee discusses, decides, and reaches to a on whether you pass the events. Okay. So this involves like intense discussions where committee members like evaluate the work and ask questions. So I think this is how I imagine the process works based on what I have observed and learned from my colleagues. So just like MDT meetings in the medical field, like having a diverse and collaborative approach ensures the decisions are made based on like a comprehensive evaluation from different perspectives. Definitely, like we know, like another like a good example is like decision making and selections of a jury process. Like a jury typically include like individuals from different backgrounds, all that. So actually, go back to our topic here. So actually, I'm an NLP person. So now I have an idea. I'm not the owner of a hospital. I don't have a group of doctors, but I could have a group of like models. What if we can try to utilize multiple LLMs as virtual doctors in MDT? So the idea is to leverage, to use those like advanced capabilities of LLMs to act as the virtual experts in various medical fields. So those virtual doctors can collaborate just like human experts. And then finally, they can offer diverse perspectives. And we could call them like AI agents or LLM agents. They are the same thing. So, okay, this is the idea. By incorporating multiple LLM agents or AI agents, we can integrate like diverse expertise, leading to like more comprehensive and informed medical decisions. So our like idea comes from the agent framework. It's the first like agent. Okay, so then it goes to my first talk I will present here. It got accepted in this year's ACL 2026. And let me draw your attention to a recent article published in Nature. So it's called like Nature role play with large language models. So it's defined as like intuitively, like a dialogue agent or LLM agent can be considered as a role playing, like a single character. So this is about how agent responds given the specific scenarios. So role playing is introduced to achieve like a diversity of different like creative answers. Role playing can enable the model to mimic various like different roles you want to put. You can say like please answer like as a doctor, or you can say please answer as a like a dentist, or just different roles to enhance like user interaction. So here this is another background work. It's kind of advanced. And this is in last year's NeurIPS paper. So actually, to solve complex tasks, LLMs still like rely heavily on human like prompt. So we have a prompt. So which also brings huge challenges. So Camel, this work proposes a new multi-agent framework called role playing, and it's like they have two components. One, you can say here they have an AI user, and they have like an AI assistant. So they have like what they did is they do task-oriented role playing and includes so two parts, two agents here. And so here how it works. So AI assistant and an AI user, so they will collaborate to complete like a special task through multiple rounds of dialogue, like conversation, until the AI user thinks like the task is okay, it's good. So on the one hand, the AI user is responsible for providing instructions to the AI assistant and guiding the dialogue into the direction to a task completion. And on the other hand, the AI assistant needs to follow the instruction given by the AI user and make answers and provide solutions. So this is the workflow of those like multi-agent. So here's an example of stock trading. So, but this is different from what we want to do, definitely, because like you can tell that those two agents here, the AI assistant and the AI user, they don't have like clear difference in knowledge. So let's turn our focus to the core matter, like actually we're in a medical school and So this is covered in Google's DeepMind paper. It's called like large language model encode clinical knowledge. It's published in Nature in last year. So the main contribution of this work includes two parts. So first, they propose a standard like evaluation data set in the medical field. It's called like multi-med QA. And the second one, they train a model but it's a closed model. We cannot call it, we cannot use it. So it's the corresponding sort value, and which achieves the result like even better than human expert. So we can take a look at our our data set. So this is what it looks like. So we have a question, and we have some 4 options here, like A, B, C, D, and we have the evidence. So actually, the data set is a collection of different evaluation data sets, including like Math QA, PubMed QA, QA, MMLU, and maybe some of you are familiar with those data sets. So among them, like the first, they have 7 data sets. The first 6 data sets are like currently available public data evaluation, and Google has just sort them out here, and they provide another one. The last one, they create a new one. So say the example here. So they provided a medical question answering data set and data set. So each question is given, and they have like multiple choice options, and LLM are tasked to to select the most accurate response. So based on this question, we have some we can say some like major challenges here, like which hidden like LLM from handling those medical tasks. Yeah, so first, I think due to the challenge, we know like privacy issue. So due to the cost and privacy issue, the amount of training data for medical question answering are limited, because like we have a lot of data in LLMs per training, like a huge amount of data. But for medical field, we don't have that much. And secondly, like those high performers requires deep domain knowledge and like complex reasoning capabilities, like which raises the requirement for LLMs to handle medical tasks. Yeah, those are background questions here. This is what we're going to do. Okay, so we have shown a lot here. We have shown a lot of like background here, and recent research has shown like promising development with LLM-based agent. And the design of our work, like we call it like MediAgents. So this like multi-agent collaboration stands out by simulating the human activities. So we believe that this approach can inspired by those. Inspired by the above ideas, we propose a multi-agent framework called MediAgents in a clinical domain. So this is a training-free and interpretable manner.
Yes. So I can. Oh, over there. Okay. Okay. All right. Thank you.
Other like online people say.
Sorry for muting you. If you want to ask any question. I don't know. Okay, so actually here you can say we have like 5 steps here. So first, we want to get some experts, right? Okay. The first step is like we get some experts from distinct like domains according to the question and answer. So we extract some keywords and use that keywords to get some knowledge, different experts. And then, like the second stage, those domain experts put forward their analyze, like with their enterprise, with their knowledge. And the third the third stage here, so we call it like report summarization. So those we have a final expert. It compose or summarized report based on those series of timelines. And finally, the fourth one is called collaborate stage, and it engages the experts in discussion over the summary. And the report will be revised iteratively until the agreement from all experts is reached. And finally, we have decision making to get a final decision, based on the report. So this is an example which represents an example instance from our data set. So it's much more clear, maybe. So here you can tell that we get a clinical question. This is about a 3-month-old infant having difficulty breathing. So here now we have from this side we have 6 experts. We have some experts from question, and we have some experts from the options. When we do a test, we can look at the option and we know what are those. We can guess what are those domains might be useful. And we have some 6 experts cardiology, pediatric, and different domains. And those experts analyze the condition. And then here you can say each expert, they have their own analyze, and they have an initial report. And some of them might disagree with the report, and they will give a suggestion. And then we have a second round revision for the report, and we have multi-turn discussion. So a final report is produced. The best represents those experts' collective knowledge and reasoning about the medical question. So go to our technical part framework. Okay, so given a clinical question queue and a set of options OP, O1, O2, OK. So K is number of options. Normally it's 4 options. The goal, the expert gathering stage is to obtain a group of question domain expert, it's QD. And also we have option domain expert is OD, QD and OD. So we assign a role to the model and provide instruction to guide the model output to the corresponding domains based on the input question and options. Yeah. So here, RQD is the prompt QD, and ROD and prompt OD stand for the system role and guideline prompt to gather domain expert for the question Q and option O. Okay, this is the first stage. And the second stage, after gathering the domain experts for the question O, for the question Q and option O, we aim to ask those experts to generate a corresponding analyze, prepare for later reasoning. Okay, so in the third stage, it's called report summarization. We attempt to summarize those analyses from various different domain experts. So given a QA, OA, is a question analyzed and option analyzed, ask the LLM to play the role of a medical report assistant, allowing it to generate a combined structured report. Okay, and then the fourth stage is the collaborate discussion, or we call it consultation. So since we have an initial summary report O, and the objective of this stage is to engage different domain experts into multiple rounds of discussion. So finally, render summary report that is organized, each expert thinks it's okay, it's good. So during each round of discussion, the expert gave their votes, yes, you can say here, the vote is yes or no. Yeah. And if say vote for the report, and you have yes or no. And if the vote is no, and the report will be revised, and the agent which gives the vote for no should give a modification opinion, like suggestion as well, opinion as well. So in this way, the discussion are held like until all experts vote yes, and the final report for the discussion never attends the we set like 10 times. Like we should not do like more than 10 times for the attempts. It's a source of. And the table summarizes the data. So we have different like data set. Some of them are huge, some of them are small. So more information about the data set is presented in our paper. And yes, and different data sets, they have different formats. Some of them, they have like questions and answers, and some of them also provide a paragraph of context. Okay, and this is our final result. You can see here, there are definitely different roles, and it's hard to explain. Let me tell you. So we have like MedQA, MedMCQA, PubMedQA, those are different data sets. And we have like some baselines. We have like few short COT, and few COT and essay. Let me explain. So few short introduced like that. Maybe you know what is few short. It includes some like template demonstration. So we add those few short examples into input question. And COT means like we have the prompt. Say like let's think step by step. So after the question to enable better reasoning. And SC means self-consistency. So this is an additional sampling method based on the majority answer by sampling multi-chance or multi-times. Yeah. So you can tell like that our MediAgents is a zero-shot setting, and actually it outperforms all other settings in zero-shot. And even it is, if you compare it with few short COT and SC, sometimes it is better. So interesting, if we introduce COT, sometimes it leads to a bad performance. We have found that COT can result in hallucination, typically associated with misapplication of medical, like those concepts or terminologies. So in contrast, our MediAgents framework effectively mitigate those issues. So we have GPT 3.5 based and GPT 4 based, both of them are the sort of. So okay, so for the main, apart from the main result, we also do some application study. And you can tell like definitely we have like different stages. We have 4 stages, 5 stages. So we do an application study on 3 major stages like analyze, composition, report, categorization, and collective, and finally is consultation. So it's those 3 lines. So you can tell different stages, like all of those stages are non-trivial. We also conduct another experiments here. So it's like people may ask why we only do 3.5, GPT 3.5 or GPT 4. Definitely, we have experiments on those like old, like open source models, like including MediAgents, Biomed GPT, like Biomed LLM, and BioBird, and old like older like Cybird or Bird. So you can tell like those are too bad. It's like we don't want to choose them as the base model. Okay, so the second application study here is, as our MediAgents framework involves like multiple agents that play certain roles to get the final answer, we explore like how the number of agents influence like might be influence the overall performance. So we change the number of question and option agents to observe the performance. So there are some features. So first, you can tell the key observation is that the performance improves significantly with the introduction of any number of agents. Like no matter we have 2, 3, 4, 5, it is all better than they are all better than the first one, one agent. Yeah, and we also find that the optimal number of agents is kind of consistent across different data sets. So it's around like 4 to 6, and for option agent is around like 2. Yeah. So which means like we might be able to use this setting to other different data sets beyond our testing benchmarks. Yeah, and we also investigate the influence of agent number changes. So we perform additional studies. Like we delete, you might think like how will be the performance if we delete the most relevant agent or least relevant agent, or we delete randomly. So you can see results show that there's a minor variance for different sizes of data with random removal. And to further explore the effect of agent quantity without changes in domains. So we say here, so you can see these 2 lines first, these 2 rows first. So we conduct this experiments with 6 like identical domain agents, and then we have 5 like same identical domain agents and 4, and you can observe the performance shifts. Okay, so based on our result, we also conduct a human validation like annotation to identify limitations and issues in our model. We have like category 4 types of errors in like this table. So like first one is lack of domain knowledge, and second is like misretrieval or domain is like misretrieval. Third one is consistency, and fourth one is COT errors. So you can tell like to analyze this error, we randomly select like 50 cases from LLM and MCQ dataset, and we get this percentage distribution across different error types. So you can tell it's bottleneck in our proposed MediAgent framework. The major one is the misretrieval, because we do not train our model. So one potential solution is to incorporate useful medical knowledge resource. So this is also another final result example. Like you can tell, like for the first report, this is the initial report. So actually they have a wrong option here. So it's they have 5 options, and definitely the first option is the option A is the correct one. But for the initial report, it gets the wrong option. And after some discussion, and it shows like we just have to correct this report, and it might be useful in medical school, and it is very interpretable. Some takeaways, like definitely this is the first MediAgent multi-agent framework in medical domain, and we think like we do role playing, and we don't need to use RAG RAG, and we can get some knowledge from this model. And in future, we think like role playing might be more useful. It will empower LLMs to do more complex tasks like lab automation. Our paper is available on arXiv, and our code has over like around 200 stars, and here has like it has been significant engagement on Twitter with like many retweets, likes, and views. So any questions for this?
I guess it's very interesting work, and also I have a question about so you do the testing against like GPT 3.5 and 4. now, like, you know, yesterday we also have like Llama 3.1 and other. Then to do any further testing on other open source model or?
Kind of, because like this paper we submitted around like last year is like December. So at that time, I should just use those models. But definitely, I think you raised a good point. Like we can test Llama 2 or more advanced like open source models or like your models.
Yeah. In our lab, we also have those Llama and other.
But it's like after our research. So definitely we should try that.
Yeah.
It might be interesting.
Okay. Any other?
Yeah, so I think the motivation of this work is we don't want to train anything. So just like we think LLM during the pre-training stage, they learn something in the medical knowledge, medical domain. But if you just use like traditional prompting or even like better COT, it will be used like it will be not useful. And we use this multi-agent framework. We have multiple discussion like human do. Like then we can like get those knowledge from the pre-training. And then this is the reason we don't want to do any training.
First one you can tag in.
Jeff, do you have any question?
Okay, no, that's fine. So
Yeah, I have a question.
okay, yeah, Dr. Xie.
Yeah. So, we actually have currently conduct a project related to a diagnostic reasoning task, which is more related to the realistic clinical application task, rather than like the QA task than in the NLP domain. So, based on the MediAgents framework, but we currently found that we tested zero-shot performance. Even GPT-4, its performance, its accuracy is still very low. So the task is like you input the patient history on from the case report of the patient with the patient history. You would like the model to predict the top possible diagnosis or final diagnosis or differential diagnosis for this patient. So currently the top 1 and top K accuracy of even GPT-4o is still very low. So do you have any ideas like the MediAgent framework like can be involved in such realistic, challenging tasks to improve their performance? Yeah, thank you.
Yeah, this is a really good suggestion. So we really want to try those real diagnosed data sets in hospital, but we don't have this access. But I think if you want to increase the performance, there are a few ways. Definitely, what I said, like a MediAgent is a kind of solution, potential solution, and also you can try retrieval augmented generation. So you can have some source, and you can have some demos or examples. It can retrieve similar like context or description from your source knowledge base, and you can use that for your better reasoning.
Yeah, get it. Yeah. So for the data set, actually there are several sources like NEJM and the JAMA. They have many the challenging clinical cases uploaded by physician online that we can use for testing.
Yes, so
Yeah, I think it's always good to have more data sets can be tested.
Yeah, we will try retrieval augmentation. I think it's a very useful suggestion.
yeah, so the one paper called like MedRag. It's like in Dr. Lu's like NIH lab. You can check their paper called MedRag.
Get it. Okay.
Yeah, thank you.
Okay, so I can move forward. I do have some others. Yeah, so maybe I can try to speed up. So this is another personal story. So I mean, definitely I want to move forward. Like, I received an email like when I did a teaching fellow for SMITA, like deep learning course, like CPSC 452. And I received this email from students that it turns out like the issue is too super simple. It's just a simple syntax error. So I'm sure like many of you have faced like different code problems and bugs in your daily research and work. So none of us starts out being an expert in coding. But this is where having a code LLM becomes meaningful. So it can offer some help with like debugging or even writing for code for you. So it is like an old task for natural language to code. Like early work in 2021 translate like natural language problems like text descriptions to circle like program. Like this is EMLP 2020. Even in the early the EMLP 2018 paper, like by like our late professor is like Xiangru lab. Yeah. And recently, a lot of people show like those pre-trained LLMs, like based on code, like code pre-trained on code, can produce Python code to tackle like programming challenges. And there's a science paper like pretty famous. It's called like AlphaCode, like by Google DeepMind. So they just this the first model that could outperform many human programmers in some task. And we all use OpenAI or GPT to write code. Maybe how many of you have written code with GPT before? Yeah. Okay, a lot. Yeah, a lot. Yeah. So I think it gains a lot, like massive, like probability over the last 2 years. Like we have code pilot. Yeah. So this is a task of like code completion, and it's a feature offered by some IDEs and text editors. So this tool is more than like just filling the blanks. Like it can write to generate the whole functions like classes, methods, and like the whole code blocks. Yeah. So just in a conclusion, like LLM can generate the functions or classes based on a given prompt. So there are lots of like code models right now, like CodeNama or like StarCoder or DeepSeek Coder. And there's some existing famous human evil like benchmark like human evil and DS like 1000 and BBP. You can tell like they have run like the best model could like GPT-4 could do like 80% of those tasks, which means like give you 10 examples, you can solve like 8. So it's pretty like promising. And recently there are a lot of like new interesting hot topics in this area. Like say like there's a something called like Devin, and it has like value around like 2 billion. Just they release like AI developers. And recently we have a like open Devin project. It's a community project to release maybe today, and it get a lot of like stars on GitHub, like around 25K stars. So and also like there's another popular aspect to teach LLM to use how to use tools. For example, they can learn to check the weather and use the Google weather and use the calculators and other APIs, Google APIs, or like RESTful APIs. Like here, they can use different tools to in the UI like when you chat with ChatGPT. Yeah, to solve a complex task. Yeah. So actually, this is one of my motivation. Is like different from general algorithm. Like this is a sorting algorithm. So here's what we do. Like we do computational biology or bioinformatics. Like we involve a lot of like domain knowledge, like system biology or like proteins, proteomics. Yeah. So this is the work. I will introduce this pretty quick, briefly, because I don't think I have too much time. Many of you have like used like write code in your research with GPT before, but we also want to know like in many situations like they do not perform well. So what are those situations and how can we analyze the limitations of current LLMs for bioinformatics? So we have this like we present a benchmark to address those issues. Like this is a bioinformatics code generation benchmark. Yeah, this is a kind of a workflow, like how bioinformatics code generation. Like we have to learn, we have to read books, we have to learn those background knowledge, we have to learn how to code, and this is a kind of a blast workflow people implement. So we show like building this benchmark, like it's called BioCoder. So it's a challenge benchmark to examine the coding capabilities of LLMs. So we have like some tools like parsing tools, and we have the data, process data, we have testing and Docker to execute the code, and we have our models. So this is how we get our data set. Like we use the real journal data set. Like we have like in Nature, like we have code associated with the paper. So we extract the code, the repository code from those journals, and we have like a ranking of program language. But definitely this will not exactly reflect the real world capability of language, because like like it's in research code, but we need to kind of just want to investigate the Java and test it here. So this is our prompt. Like we gave a kind of a description, like we have some declarations, and we have a summary. This is the prompt. What do we want the model to do? Like we want to return a string with the sequence in fast format, like parameter. This is the parameters. Yeah, it's like two faster function, and we want to generate this function. This is the whole thing we feed into the model prompt. And then we use a Docker. We use some Dockers to execute, and whether we have like success or fail. This is easy to understand. Okay, so we have different models. So we call it like I described StarCoder before. They have different models. Definitely, like last year, we saw a lot of models with like 128K like context lengths, and even up to 1 million context windows. But well, this work was like completed. It's finished before the development of large context models. Like so, we have only like 8K context limit. So and we use pass K to evaluate. So it's a matrix like defined in DeepMind science paper. So it's like you can try multiple times. Like just say you can have 10 tries, and just like if you have one try, it's like top K generate. We have like we can do sampling. Like you say like you can try 10 times. It's past K, and just like if you have one time generate the correct program, the correct code, and we say it is a successful generation. So here are the results. So we can tell like we use like GPT-4 3.5, StarCoder, CentaCoder, those different models. And you can tell even like we use GPT-4. GPT-4 is like by far the largest model we tested in the study, and dropped all other models in terms of size. It will only achieve just like slightly above 50% in terms of even like past 20. So like with like past 1 score of like 38. So meaning that like only 38% of the code passed on the first attempt. Yeah. So actually why this is interesting, because like I just show like in like general domain, open domain code generation benchmark, you can get like around 80% accuracy. But here, bioinformatics code generation is super hard. Even you can tell like for those small models, like StarCoder, those are all code LLMs. They do not train it on the word knowledge, like large amount of pre-training data set. So they can only get like 4 or 5% accuracy or plus 1. So this is interesting. And we say like, it seems that the additional context and domain knowledge requirement is the main bottleneck for those models. This is a simple idea we want to benchmark bioinformatics code generation. If you don't have questions, I will. And there are some like summary and future work. Definitely, like it's the main challenge is no input, like the context limit. Right? And the second challenge is like how to do. Okay, we can write code, and like I'm not doing wet lab, but for wet lab people, they kind of need to write code to the robot, and the robot will operate in the real wet lab. And if you want to, you can generate the code, and you can operate in real robot, the wet lab experiments. And there's a Nature paper recently, they call it like autonomous chemical research with large language models. Yeah. So also we have a benchmark, it's called ML bench. It's called like, what we do for biocoder is we all do experiments on like large language LLMs instead of just, we don't do anything on agent. So we want to test like agent on this like machine learning task. So we just described human eval before, like this is simple, like give an instruction and generate a function. It's just simple. But normally, like when we write code, I did not write code from scratch. I use some existing packages like libraries, like repos. I use like MATLAB or PyTorch or like NumPy. I don't write it from scratch, right? So this is interesting. Like real world programming involves like employing those existing libraries to do tasks. So what we did here is like we have a ML bench. It's like we have two settings. One is for LLM testing. We call it ML LLM bench. One is called ML agent bench. And so here you can tell this is the human eval. You only have the input instruction sentence and you generate an output. And for this is like a repo eval. It's like you give a repo information and you have you mask a function and you want to generate the function. And for this one, what we have the difference here is for ML LLM bench. So we also input the whole repo and to say, given the repo, how should I use this repo to call this repo, to write a code, to operate this repo, and translate this instruction to like a script, Python script. But for the agent part, what's the difference here is like we don't have a like instruction. We don't say, you can tell here, the instruction is quite simple. We don't say like, we don't ask the model to translate the instruction, but we ask the model to navigate the whole repo and to learn how to write or say here. It did not generate the script, the Python script. It generates a kind of bash. So the bash will say like, first it will read this Python code is cat. The agent uses cat to read this code, and then it write some lines and use this lines as the output. And also it learns how to install those like pre-existing requirements. If you want to download a model, right? If you want to download a repo, you have to install those requirements. So for this setting, we provide the whole Docker. Like the model just needs to write a code and then we can execute it. But the thing here, in this ML agent bench, the model the agent needs to first download the data from Hugging Face or from other source, and you need to download the model from Hugging Face or from other source. And and for example, say it wants to use MeNama, and it will just go to MeNama's repo and navigate the repo, like learn what the structure or the code structure looks like, and try to look at some like cat, ls, or cd, some files into that repo. And this is quite interesting. And this is definitely why we need the ML bench, because like definitely it's like we want to bring a more challenging task. We need to understand the code structure and the document, like a README, because each repo they have a README. And like definitely we want to do some like practical task. So this is an example. Like we have ESM4. Definitely we all know ESM4 is like a Facebook repo. And if you want to do ESM4, you can use that. You don't need to write code to do protein folding. You can just use this ESM4 code, right? So you go to that GitHub code and you have this instruction. This is example. Okay, so this is our instruction, the input. This is the input. And then what the agent will do, the agent will first locate the README, because the README file is a huge known file. It has multiple tasks, but maybe we just need to use like several lines of the README. We don't need to read the whole README. So it will locate first. And then it will locate the example code in like if you want to do structure prediction. There might be a structure prediction, or like they have like protein folding or inverse folding. They have different tasks. we want to locate which task example code we want to utilize. And also it learns like we need to change some kind of like arguments, like it will navigate the code to say how to add arguments. If you want to add a new data set, you want to add an argument. Okay, so this is how we build the data set. Like we have some, we have around eight CS graduate students to annotate the data set. It kind of time consuming. For each task, we have around like 5 hours. So it takes like around hundreds of hours to annotate the data set. And we have like, first we select the README and write the instruction and write the ground truth code. And people will also do the quality check. Okay, so we have like around 18 repos here. Definitely we have like biomedical models, like we have medical zoo, it's a computational vision models or like repos, and we have ESM. And for other models, we have like, you say like we have diffusion models, we have like graph models, we have like TensorFlow, like or time series library, we have a lot. Like we have like diverse, a huge diverse different data set, different models or repos. So then we have like around 9,000 examples from those 18 GitHub repositories. Okay, so and also like we have different settings. So for the LLM settings, since like we are not asking the LLM to locate the correct location, but we have a limit of the input. So we have to do some different settings. First, we say like we can do BM25 retrieval, and we can do like the README, just trunk the README, and then we can have the oracle. Oracle means like we let the students to annotate which part is the ground truth, the reference that we will use. We use that oracle information in that. So you can tell this is the example. So here, this is the result here. So you can tell we have GPT-4 here. Yeah, we have different settings. So oracle, code, and retrieval. Code is the whole thing, like trunking. And BM25 is the retrieval, and oracle is the ground truth, like human ground truth. So you can tell definitely like GPT-4 is the best one. And this is everyone knows that. But it is much better than those like open source models like CodeLlama or DeepSeek Coder or Llama 2. And GPT-4o, like it has like it is still a challenging task. You can tell like Oracle is better than code and retrieval. And retrieval here is kind of bad because we think BM25 might not be a good retrieval task for this repo level code generation. Yeah. And also we fine-tune a little bit. We fine-tune the model and we fine-tune the LLMs, and we have different settings. You can say what is the difference between out of distribution and in distribution in our paper. But anyway, we fine-tune it, and it shows like it's better than like non-fine-tuned one. Okay, there are some results on agent one. So we do agent, but this is kind of interesting. Like we used some recent famous agent framework like Swing Agent, either OpenDevi. So actually you can tell this is success rate because we don't do like pass 1 and pass 5 here. You can generate multiple times for LLMs, but for agent, you don't need to generate multiple times. Just it will execute by itself. So we have the success rate, and it was like much better than LLMs before. So agent actually kind of solved this task. So we have different base models. We have GPT-4o or GPT-4 for base models, and we have different frameworks. Those are different agent frameworks. You can tell OpenDevi is kind of like they have a difference between different agent frameworks. Yeah. Okay, and it costs a lot. Yeah, and this is how the agent works. Like you have a instruction. You say you want to use this convolutional GAN, like for a minute handwriting digital classification, and you have some learning rate, like epochs, batch size, and you use this like prompt, and you have a like the agent will do several things. Those lines of code, they are all written by agent. Agent first will run the Docker and it will create a file. So the agent wants to create a run.sh file, and then it writes the script. The agent writes the script to put them into the file. You can see it gave access to that file and cd to that file and run it. And it failed. Okay, it has the error. What's the error? Because the agent did not download the dataset. So it don't know what is this like minutes dataset. Okay, so it tried to download the dataset from Yandequan's like website. Okay, so this is how it works. And finally, then execute it again. So execute it first time, have an error, and try to solve this error and execute it again, and it solves. Okay, so this is interesting. Like we see like we might use AI agents as scientists, because we see like about those tasks, the ability of AI agent for like is like far better than like LLMs. Why? Because agent can choose which file to open, which file to read, and it can call some IDE tools and compilers as like a human. So AI agents, like when integrated with some like lab frameworks, platforms, can operate like at varying levels of like those different levels. Like this is defined by a paper. Like they have like 3 levels. Definitely, I don't know where on the final level, but if we have a final level, we don't need to do anything. We just let agent to do research. And also, like agent can be kind of conversational systems capable of like coding and reasoning, and that coordinate LLMs, machine learning tools, and lab platforms, and even like a combination of them. So, for example, AI agents can write code to operate the robotic hardware for physical or chemical experiments. But here, I described this paper before. So they have called a robot chemical research, and it's the GPT-powered chemical research, and it can design some reactions and it can make drug. And finally, we have a small paper. It's a perspective paper. We want to highlight the safety. Like we know, like if we can do the agent can do experiments. What if it can make a bomb and make some drug, right? So it's a huge safety problem. And there's no work existing. There's no work to define this error or safety problem. We have a framework to analyze it, and we propose like kind of a solution. It's like agent alignment, agent regulation, and human regulation, 3-part like problem solution to do the risk mitigation and oversight mechanism. And this is our classification of the risk. So for this subgraph A, so we have like the risk classified by the origin, like the user intent, including the direct and indirect intent, as well as the unintended unintended one. Okay, and the graph B is the risk types classified by different domains, the scientific domains of agent applications, including like chemical, biological, different like things. And graph C, subgraph C, we have risk types. So they are classified by the impacts of outside environment, like human health, environment. And we also divided the different source of the problems, the safety problem issues from the agent workflow. Like we have like tool usage, and we have planning, we have action, and we have like the base model memory and knowledge. Okay, so this is kind of, I just reached time. So this is kind of the reference of what I described in this talk. We have 4 papers, and bad agents, biocoder, ML bench, and a perspective paper on risk of LLM agents for science. And finally, I would like to give a huge shout out to my collaborators and Gerstein Lab and my advisor for their support and like contribution in this project. Yeah, any questions?
Yeah.
Okay.
Any questions? So
I can share Zoom. Yeah, share.
I wanted to ask about the MediAgents paper. So you did some testing in the number of agents that you use for the questions, right? And you saw that there was a trend going up and then going down.
Yeah.
I was just wondering if you expect that smaller models or open source models would outperform the larger models with a lower number of agents.
Yeah, I think this is one missing experiment we did not conduct, because like you can use different size of models to act as different experts. You can say like we have a GPT-4 as the agent, we have a Llama as an agent, we have like Llama as an agent. So what if we mix them, and what would be the performance? I think they would be interesting like topic, but we did not.
And this is very basic because I haven't worked with agents myself. How do you create like an expert? It's just like a prompt that you modify and put in the beginning for the next generation.
Yes. So we have a prompt. You can check our paper and our code. Like we have released the code. So we have a complex prompt for different domains.
Just the last. What would you think that would happen if you apply the same strategy for the MediAgents, having different experts, to the problem of coding?
Sorry, ask again.
Like, I'm just thinking of the graph that you showed, like the performance, the accuracy going up, and having this consensus board. And what if you tried to create a consensus code?
Code.
For code, yeah.
Yeah, I think this is a good question, because here, so we have a lot of work. We have this world. They have a lot of people like they are doing code generation. I'm not a person working in code generation, and in code generation there are a lot of like agent work, and also there's another field, this multi-agent field, and they do like reinforcement learning, and they do a lot of like language model based multi-agent. And those people, they do a lot of work. You can search. There's a paper called MetaGPT, the MetaGPT. MetaGPT. They use like multi-agent in code generation. Yeah. So there are a lot of work in this field. Thanks, but it's a good question. Thanks. Okay.
I arrived a bit later when you were talking about the MediAgents paper, but I was just wondering. I think you hinted a little bit about retrieval, like misretrieval, like some problems that you run into. I was just wondering, did you consider using like knowledge graphs, like RDF technology, to help with like retrieval like processes where? Because if I understand, sorry, I haven't read the full paper, but it seems like there's a lot of like role playing, multiple agents like working, and I know it's like fairly new, like with the way people are applying knowledge graph, like graph technology to retrieval stuff. So I was wondering if it's something that you considered while you were.
Yeah, I think this is relevant to Chen Chen's question. So it depends on what knowledge graph or like kind of medical source you have. Like, because like it kind of like a huge cost to build that knowledge graph in medical domain, and you don't know whether it works or not work. So and you have make people to annotate those knowledge graph. You cannot do information extraction like automatically. So I think if you have a good knowledge graph for medical domain, definitely it will be beneficial. Yeah.
thank you. I think we ran out of time. So
Thanks. Yeah, thanks.
Yeah, thank you all.
Okay, thank you for listening for the